Today we're going to look at the next topic in integration, which is finding antiderivatives of functions involving trig functions. So let's take this as an example. We'll do lots of examples today, kind of get more complicated as we go. How would you go about finding the antiderivative of that? And I'm going to be leaving lots of these for you to finish, but I'll get you started on them. So, each one of these is a small step from the previous one. So let me encourage you, turn off the video rather frequently during this talk and see if you can figure them out on your own. Learning mathematics is good. Being able to see how to do it and practice it and do it yourself is even better. And so think of each one of these as a game, as a little challenge, and see if you can do it on your own. And then I'm going to give you the answer, but each one of these is very, very doable. This is one that you could have had in Calc 1. The way to do it is just to let u be equal to sine of x, and then du is going to be equal to cosine of x dx, and so it's a simple substitution. U to the 6th du, and of course that's going to be 1/7 u to the 7th plus c, which is 1/7 sine to the 7th of x plus c. All there is to it. Okay, well, there's the first one. Let's try the next one. Okay, heed my advice. Try to do it on your own. If I have to show you, it's just a little bit of a failure because each one of these things is very doable. Okay, you look at this one compared to this, and you say, what's different about it? Here I had a nice du standing right in my face. I'm pretty close right there. Do you see why? Because I can write this as the sine to the 6th of x. Cosine cubed I can write as cosine of x dx. I pulled one of them off and I'm left with a cosine squared left. Agreed? Cosine squared can be written as 1 minus sine squared. Agreed? Cosine squared is 1 minus sine squared. So I do the same substitution as before, and I'm just going to get sine, I'm going to get u to the 6th times 1 minus u squared times du. Of course, there you can now multiply it out. Going to get u to the 6th minus u to the 8th du, and I'm going to let you finish it from there, right? Take the antiderivative, and then once you have the antiderivative, then you substitute back in for u as sine of x. See that? So that's just kind of a small step from the previous one. Okay? What if you had, for example, another small step? What if you had sine 6x times cosine to the 5th of x dx? Small step. Can you see it? Same as before. You're going to get this. You can factor off a cosine of x dx, and I'm left with cosine to the 4th. Well, cosine to the 4th is the square of cosine squared. Cosine squared is that, right? There's a cosine squared, and so if I square that, I've got cosine to the 4th. See that? And now I just put in my regular substitution, and we get what? Going to be u to the 6th, 1 minus u squared quantity squared du. Now you can just multiply all this out. It's going to be what? 1 minus 2u squared minus, plus rather, u to the fourth du. Multiply it all out, take the antiderivative, stick it back in. See that? What if I had, let's change the rules. What if this were cosine to the sixth x, and then sine to the fifth x dx? Okay? Then, notice the key here. Do you see the key? Here I want to let u be equal to cosine of x in this case, because then du is going to be what? Minus sine of x dx. Do you see why that's so important? So that means I can pull out, I have an odd number here. Do you see what's going on? I have an odd number. Since I have an odd number, I can factor one of them out. That's what I'm going to use for my du. I factored one of them out. I started with an odd. By factoring one out, I now have an even. I have an even number of signs, and as soon as I have an even number of signs, I can write that as sine squared is 1 minus cosine squared x. There's sine squared, and now if I square that, I get sine to the fourth. So this is sine to the fourth times sine is sine to the fifth. And now you multiply this all out. What are you going to get? You're going to get, if you put it in terms of u, you're going to get u to the sixth, 1 minus u squared, quantity squared, sine of x dx, that's equal to negative du. So bring the negative out front, du, and you're all set. You have the same thing as you had up there. Okay? So the key is taking that odd power of sine or cosine and pulling that sine or cosine off, and then writing the rest all in terms of the other trig function. Okay, that was the key. Okay, so what if you had odd of both of them? What if you had, let's just take an easy one, sine of x cosine of x dx. Okay, they're both odd. So you have your choice now, right? You can let u be equal to sine of x, du is equal to cosine of x dx, and so this becomes what? U, all this is du, antiderivative of that is 1/2 u squared plus c, which is equal to 1/2 sine squared x plus c. Agreed? On the other hand, I had the option. I have an odd number of both, so I could have let u be equal to cosine of x, then du is equal to negative sine of x dx. So what's going on now? Cosine of x, that's my u. Sine of x dx, that's equal to negative du. See that? So that's going to be negative 1/2 u squared plus c, which is minus 1/2 cosine squared x plus c. Whoa, what's going on? We did it both ways. Both ways seem totally legit, and yet look at my answers. This way I got this for an answer, this way I got this for an answer. What's going on? How can I get two different answers depending on the way I did the problem? Do you see what's going on? Turn me off and think about it for a little bit, because I'm going to tell you. The answer is that sine squared x plus cosine squared x is equal to 1, right? That's what we've been using. So 1/2 of this plus 1/2 of this is equal to 1/2. which means that 1/2 sine squared x is equal to negative 1/2 cosine squared x plus 1/2. See that? I've got this and I've got this. Look at here. Those two things differ by a constant, which is fine. See that? They both have constants on there. They differ by a constant. As long as they differ by a constant, that's all legit. So there you go. Cool, huh? So the point is, if you have an odd number of one or the other, you're all set. If you have an odd number of both of them, you can take your choice. What happens if you have an even number of one or the other? Let's take the simplest possible case. Let's just take a cosine squared x dx. By the way, what if this were cosine cubed? Again, just to be clear, what if you had cosine cubed there? No problem. You've got an odd number there. So I can write this as cosine of x dx. I'm left with cosine squared, and cosine squared I can write as 1 minus sine squared x. Agreed? So even though there's no signs staring me in the face there, they're still kind of hidden in there, right? So now I can let u be equal to sine of x, and I'm left with 1 minus u squared du. You can go from there. See that? So no problem doing that. What happens though, as I say, if we've got an odd number instead? I'm sorry, an even number instead. Now what do you do? Now you can't factor one off. So you can't let u be equal to cosine of x, because if you did, you have your du is equal to negative sine of x, and there's no sine of x there. If I wanted to, I guess I could factor off. I could write this as cosine of x times cosine of x dx, and so I could let u. How could I do this? I could let u be equal to sine. How do I write this in terms of sine? I would guess I would need something like cosine squared x plus sine squared x is equal to 1. And so cosine squared x is equal to 1 minus sine squared x. And so cosine of x is equal to the square root of 1 minus sine squared x. So I could do that, and then I let u be equal to sine of x. Du is equal to cosine of x dx. Let's see once what happens. So this cosine I now write like this. Okay, and now I can make this substitution. The problem is, that's not an integral that you know how to do, okay? It's one we'll learn later, but it's kind of involved, and it's kind of going backwards in order to be, it's not the direction we want to be going. Given this, we want to get it in terms of sines and cosines. That's how we're going to handle this thing, is to get it in terms of sines and cosines. So that's not helpful, okay? By the way, if this were an integral from 0 to 1, it would be helpful, because that's just the top half of a unit circle. So if that were from 0 to 1, that would be a quarter of the circle, which would be pi. A circle of radius 1 is pi, and so this would be equal to pi over 4. So if we had particular limits of integration on there, it'd be nice and easy. But in general, we don't have the antiderivative. So anyway, that doesn't work. So what does work? What does work when you have cosine? And the answer is, go back to what we learned at the very beginning of Calc 1 in Essentials, when I taught you that the sine of a plus b and the cosine of a plus b, and that couple, the formulas for that. Remember, I think I told you the jingle. Sine, cosine, cosine, sine, cosine, cosine, sine, sine. sine, cosine, cosine, sine, cosine, cosine, sine, sine. And you put A, B, A, B, A, B, A, B, and you put a plus in the top one and a minus in the bottom one. So those are a couple important trig identities. And then from that you can say, okay, what's the cosine of A plus A? Which of course is the same as the cosine of 2A. And so if you use the formula, you're going to get cosine A, so it's going to be cosine squared of A minus sine A, so it's going to be sine squared of A. See that? And so now I can write cosine of 2A is equal to cosine squared A minus sine squared, of course, is a 1 minus cosine squared. So I've got that. And so this is equal to cosine squared plus another cosine squared is 2 cosine squared A minus 1. Which means that if I solve it for cosine squared, that's what I'm after, is I can add 1 to both sides. Like that, if I add 1 to both sides, and then I divide by 2. That's going to be equal to cosine squared A. So there is a trig identity for cosine squared. And there's a similar one for sine squared. Sine squared is a minus in there rather than a plus. Okay, so anyway, for this one right here, here's what we can do. We haven't solved it yet. All we've done is used a trig identity. To rewrite it. But now we can handle it. Okay, let me get rid of all this stuff. And we're going to get, let me break it up into two integrals. It's going to be 1/2 dx plus 1/2 cosine of 2x dx. So this is going to be 1/2 x right there, antiderivative. And this is the one we did by substitution the other day, okay? If you have cosine, antiderivative of cosine of kx, that's equal to 1/k times the sine of kx, okay? Just check it out. If you take the derivative of this, the derivative of the sine is the cosine, times the derivative of this thing, which is going to be k, and that cancels with that. Okay? So the point is the antiderivative of this is going to be 1/2. I already have a 1/2 out there, so it's going to be 1/4 sine of 2x plus our constant. So that's how you do it. So that's how you do those. So notice the squares are more involved than all those odd ones. I shouldn't say squares. If you have even numbers, if you had an odd number, I'm sorry, if you had something like this, for example, goodness, you can go sine to the 4th of x times cosine squared of x, something like that, and you just have to keep using those over and over again. You write this as sine of x squared, quantity squared, times the cosine of x squared, cosine of x quantity squared. And then you would use those identities that I just told you about. This one right here is 1 minus cosine of 2x over 2. That's equal to this. So you square that. Then you're going to have a 1 plus cosine of 2x all over 2. Like that. Now you're going to have to multiply all these out. You're going to get more squareds, and when you get more squareds, you just apply those rules over and over again. So it's going to be a mess, but the point is you just keep applying those two rules, and you can boil it down to things that you can integrate. Okay, so that's that one. Okay, good. Let's do one that looks even harder. What if we put some of these in the denominator? What if you have 1 over cosine squared x? That looks tough. cosine squared x was hard enough. Now we have 1 over that. That looks really tough. Well, I make sure my computer's working here. Yep, still is. Can you see how to do it? How would you do that one? The key to that one is to realize that 1 over cosine is the secant. So this is just secant squared of x, and the antiderivative of the secant is none other than the tangent. So that one was easy, okay? Just had to notice it. Just had to notice it. Okay, let's try some other ones where we have things in the bottom. If you had, say, sine, or let's make it sine cubed of x over cosine to the 4th of x. Can you see how to do that one? Just have to be comfortable with all these trig functions. So notice I can do this one similar to the others. I can let me change it. I just don't like negatives. Let me make this cosine up here. It's down there. Okay. Then what do? I let u be equal to sine of x again. Du is equal to cosine of x. See that? I've got an odd number up there, because now I can write this as a cosine of x dx off there. I'm left with a cosine squared, but a cosine squared is none other than 1 minus sine squared, same as before, all divided by sine to the 4th. And now that just becomes 1 minus u squared over u to the 4th. Du. And that's a numerator. I can break that up. That's equal to 1 over u to the 4th du minus u squared over u to the 4th is 1 over u squared du. See that? And so this is the same as u to the negative 4th minus u to the negative 2. What do? You add 1 and divide by it, so it's going to be u to the negative 3 divided by negative 3 minus u to the negative 1 divided by negative 1. That cancels with that, plus c. Stick it back in. U is equal to sine, and you got your answer. Okay, there's that one. What about this one? Let's go back to some evens again. What if you have sine squared of x over cosine to the 4th of x dx? Now we can't pull one off anymore. So what do we do there? What do we do there? Well, I'm not guessing that you're going to figure this out, so let me just go ahead and tell you. Okay? The key when you have evens over evens is you write it in terms of secants and tangents. Sine squared over cosine squared is the tangent squared of x. And I'm left with 1 over cosine squared. 1 over cosine squared is the same as secant squared x. See that? See that? Still have the dx on there. How does that help us? That helps us because the derivative of the tangent is the secant squared. So when you have even powers, you can do that little Java. You're going to get u squared du 1/3 u cubed plus c. Stick it back in and you're done. See that? So that's what you have. That's what you can do when you have even powers divided by even powers. So the trick is, let's do another one. Just try another one. There's so many of these. This is where get yourself a good textbook and just do a whole bunch of them from the section. Each one is its own little puzzle. I'll just make one up. If I have tangent cubed of x times secant cubed x. There you go. Let's see. I think that'll work as a good example. Let's see what happens. So, the nice thing, the nice place to use tangent and secant is that the derivative of the tangent is equal to secant squared. See that? So you want to be able to use tangent and secant where you can pull off a secant squared. Okay? If I pull off a secant squared, though, I'm just going to be left with a secant to the first power, which is not what I want necessarily. Let me remind you of one more thing here before I ask you to try to figure this one out on your own. It's all these relationships between sines and cosines. If I take this whole thing and I just divide the whole thing through by cosine squared x, see that? I'm going to get tangent squared x plus 1 is equal to secant squared x. Okay, what was our relationship we had before? Sine squared, well, it's up there. Sine squared x plus cosine squared x is equal to 1. So, you know, you can put in sine squared for 1 minus cosine squared. I can put in secant squared for this. So the point is, if I pull two of these things off, I'm just left with a secant. And there's no nice relationship that just tells me what secant is in terms of other things. I'd have to use the square root there. See that? So, so the question is, what can I do here? Oops, I need a dx there. What can I do to get something I can evaluate? Well, what I do know is that sines and cosines worked well with odd powers. So let's put it all in terms of sines and cosines and see what happens. 1 over secant cubed is the same as cosine cubed, right? Oops, that's not a 3x. That's there, right? So now look at here, everyone. This is equal to sine cubed of x all over cosine to the 6th x dx. See that? See what's going to happen now? Now I'll let you finish it, but I can just let u be equal to cosine of x, and du is equal to minus sine of x dx. And this whole thing here is going to be u to the 6th down there. I have a sine of x dx, which is going to be a minus du up here. That took care of one of the sines. I'm left with a sine squared. Sine squared is equal to 1 minus cosine squared. So it's going to be 1 over u squared minus u squared, all over u to the 6th. So I can take this divided by this, and then this divided by that. Okay? So you can just kind of make them up. Okay? Just kind of make them up. So the rule of thumb I use as a general rule of thumb is if you have odd powers of things, I put them in terms of sines and cosines for the most part. There's always, and then if I have even powers of things, then I like to put them in terms of secants and tangents because of this relationship and this relationship. Okay? That's a general rule. Okay? There's always exceptions, but that's a general rule. Okay, let's see. Can I come up with one more example here? Let's just do this one. What about tangent squared? Tangent squared. What can I do with that one? Well, notice that's why it's helpful to see these relationships. Tangent squared is just equal to secant squared minus 1. Okay, and now you can do that one right off the bat. The antiderivative of secant squared is just tangent of x, and the antiderivative of 1 is just x. There you go. Okay, I think that kind of gives all the different possibilities. You can go in lots of directions with these, but that kind of does it. I got one more written here. Let's just see what happens. I've got a bunch more. I've got my notes from several years of teaching, 30 years of teaching calculus, and different times I decided on using different examples. So there's one I just have written down, but I don't see how to do it. Oops, I meant to say cosine to the 8th. Okay, what would you do with that one? It's sines and cosines, so it's even powers, so I would tend to write this as tangent to the 4th, that's going to take care of this over this, and then times secant to the 4th, right? That's going to take care of those other cosines there. Okay, now what can I do? Oh yeah, I like this one. Now notice I'm gonna put everything in terms of tangent. So I'm gonna factor off two of these. Do you see why I factor off two of them? Secant squared, because that's going to be the derivative of the tangent. Now I can write everything else in terms of u is equal to tangent. We change it up here. U is equal, oh, here it is right there. Oops, well, u is equal to tangent of x, du is then equal to secant squared x dx. Okay, so do you see what's going to happen? This is going to be u to the 4th. Here's my du right there. And I have a secant squared left. And the secant squared left I can write as tangent squared, which is u squared plus 1. See how cool that works? Multiply it through, antiderivative, and you're all set. Okay, so we did lots of them. I did them kind of fast. Okay, I could have slowed down, but I figured you can stop it and spend as much time either rewinding or stopping and trying to figure them out on your own. That's what I'm hoping you did all the way through. Each one of them is its own little problem. Okay, the only other thing that sometimes a section on trig functions does is it spends time with things like this. What's the sine of 5x times the cosine of 3x, something like that. And that's its own kind of problem. Those are especially important if you go up into differential equations and you work with Fourier series. Okay, if you work with Fourier series, this is kind of important. But doggone it, you can't do everything in a Calc 2 class, and this I've kind of stepped away from. Basically, here's what you do. You go back to those. Sine of a plus b again, and cosine of a plus b that I had up here earlier, and you play around, and you can get formulas for sine. You can get formulas. Well, heck, doggone it, I shouldn't start talking. A sine cosine plus sine cosine cosine a sine b. There's that one. I think that's all we need. Okay, let's play with that one. And then let's also play with the sine of a minus b. Play with the sine of a minus b. That's going to be the sine of a cosine of minus b plus cosine of a sine of minus b. But the cosine is an even function, so the cosine of minus b is the same as the cosine of b, so that just changes to that. The sine is an odd function, so this negative comes out front. So that becomes cosine of a sine of b with the negative there. So now we have, oh dang, so now we have these two formulas. Okay, so now you have those two formulas. So now notice that if I add these two together, I'm doing this off the spur of the moment. I'm kind of impressed. Okay, if I add these, let's get rid of this one, that one we're not using. Add these two together, notice what we get. We get the sine of a plus b plus the sine of a minus b is equal to, notice that this is the same as this, and notice that these two things go away. See that? This and this cancel. And so we end up with 2 sine of a cosine of b. This is all stuff you learn in a trig class. So the point is, sine of a cosine of b, you can write as 1/2 of that. So that's exactly what I have here. Look at here, this worked out kind of nice. So the point is, here's my a, here's my b. So the sine of a cosine of b is equal to the sine of the sum. So this is going to be equal to the sine of 5x plus 3x is 8x plus the sine of the difference, a minus b. 5x minus 3x is 2x. See that? So all the hard work here was just trigonometry. It was just trigonometry, all starting. So much of trig just starts with this one and with the cosine one, okay? And now you can evaluate each of those separately. So this is going to be what? Minus cosine of 8x divided by 8, same as we did earlier just an hour or 20 minutes ago. And this is going to be what? Minus cosine of 2x divided by 2, okay? Plus c. Plus c. Just make a trig. Just make a regular substitution there if you have to. U is equal to this, and U is equal to that. But there you go. So there you go. Now you've basically seen everything. Okay. There's how you work with trig functions. So that's this one. In the next one, we're going to use this to help us do things like this as an example. How about just as an example, x squared plus 9 to the 5/2 all divided by x cubed, something like that, where you have power roots, square roots, and to the 5th power and things like that. And so those are going to be called trig substitutions. Trig substitutions, and we're basically going to take that and turn it into something like what we did today. So lots of good stuff. You're going through lots of good integration. By the way, why do we learn all this integration? Because as I mentioned earlier, you can go to a book on tables, and you can just ask it to tell you what's the antiderivative of something like this, and it'll just spit it out for you. Now, more than likely, most of the different things like Mathematica and Maple and so on will just give it to you. So what's the reason for even learning this stuff? Are you ever going to actually need to do this to solve a problem? More than likely not. But it is important that you just see that it can be done and that how it is done. I mean, it's good to, at some point in your life, to kind of see what the process is to go from here to here. It's not magic. It's not someone snapping their fingers. It takes some work. And the most important thing, though, is that all this stuff, doing all this, just really hones your algebra skills. It hones your algebra skills. It hones your skills on trigonometry. All these things I just had over here, that all these trig rules. it just shows you the importance of those things, and it reminds you of everything. So the real benefit of this when I teach it is just to give people practice with their trig, but more importantly, just to give them practice doing algebraic manipulation, which is important in just about everything. So anyway, that's why you're doing it. Very good.